Greetings everyone. In this video, I'm going to share a way to code an animation of a Chebyshev mechanism using Wolfram Mathematica. Hope you can reproduce and analyze the code and learn something new. So let's create some functions to describe the movement of the mechanism and create its animation. Tx represents a translation in the x-axis. Ty represents a translation in the y-axis. Tz represents a translation in the z-axis. Rc gives a rotation around z-axis by an angle theta. Function E gives the coordinates of the and E of the mechanism. Transformation of a 4D vector into a 3D vector. For data section, I'm going to assign the values of the link lengths. Now, I'm going to use the functions created before to write down an equation whose solution gives us the positions of the joints and the angles of the links with the horizontal axis. T1 is a rotation followed by a translation followed in turn by another rotation of a triad that describes the contour of the mechanism. T2 is a translation, then a rotation, and then a translation of the same triad. T3 is a rotation followed by a last translation. Pose 1 represents the path of the triad. Pose 2 represents the initial coordinate system. The objective function sets that the path of the triad started at the initial coordinate system and finished in the same initial system of coordinates. The objective function is also the first part of the solution method developed by Dr. Francisco Cuenca, who is a professor at the UNAM University. Next, to find all the positions of the joints and the angles of the links in reference with the horizontal axis, we need to find an initial solution for a specific entry angle. In this case, the entry angle will be 90 degrees. Initial solution represents the second part of the solution method developed by Dr. Francisco Cuenca. Next, from the figure above, it can be seen that theta 2 should be greater than 30 degrees, theta 3 should be greater than 90 degrees, and theta 4 should be greater than 60 degrees. Now we have the initial solution values of the angles of the links, which can be used to find all the sets of solutions for each of the 360 degrees of the entry angle theta 1. Theta 2i, theta 3i, and theta 4i are the initial values from the previous initial solution section. The do command will make the entry angle of the mechanism make a complete turn, and at the same time it will find the 360 sets of solutions and will save them in solve pose, assigning in each iteration initial values from the immediate previous iteration. Once we have all the sets of solutions saved in solve pose, we can use this complete solution to simulate the movement of the mechanism. N is a 4D vector to get x, y, z coordinates along with the function 3D defined in the previous functions section. Link 1 is the first linkage as a parallel pipette. I'm gonna run the code to verify the animation. Link 2 is the second linkage as a parallel pipette. I'm gonna run the animation again to verify it. Link 3 is the third linkage as a parallel pipette with origin at the rotational joint C. I will run the animation one more time to check it. Joint 1 is the first rotational joint or the drive shaft of the mechanism. Joint 2 is the second rotational joint as a cylinder of radius 0.15 units. I'm gonna run the animation one more time to see the second rotational joint. Joint 3 is the third rotational joint as a cylinder of radius 0.15 units and whose axis passes through point C. Let's review again the animation. I forgot to call the solutions solve pose. Joint 4 is the fourth rotational joint as a cylinder of radius 0.15 units and whose axis passes through point B. Let's verify the animation one more time. I'm going to create a 3D scatter plot of points with coordinates of point E. Let's see the 3D scatter plot of points in the animation. I also want to see a flickering light at the end of the mechanism. Finally, I'll create the second part of link 2 as an arrow. In this way, we can verify that the function E defined in function section is correct. Let's review the animation one last time. A numeral symbol was missing. Let's correct and rerun the code. And this is the final result, an animation of a Chebyshev mechanism. I hope you have learned something new here. Thanks for watching.